In this video, we're going to take a look at multi-step reactions and how we can use a multi-step reaction to figure out the rate law for a particular overall reaction. So let's start out first by taking a look at what are multi-step reactions. Well, many reactions will involve a series of chemical changes across multiple intermediates and transition states. And the sequence of those changes along the reaction pathway is known as a reaction mechanism. So a reaction mechanism is going to involve one or more elementary steps. So we'll talk about what these elementary steps kind of look like in a little more detail in a minute. But a reaction mechanism with more than one elementary step is called a multi-step reaction. So, for example, in this reaction shown here, we have 3 steps. We have step 1, step 2, and step 3. So you can see here the first step happens fast, the second step happens slow, and the third step happens fast. And so we can use this information about this multi-step reaction mechanism in order to come up with a rate law for a particular overall reaction. So I mentioned elementary steps. So elementary steps are basically each of the different steps that happens in a reaction mechanism. So the last one I showed you had 3 elementary steps. And it's going to depend on the reaction how many elementary steps we have. We can define these elementary steps through a term called molecularity. And essentially what this is the number of species, so it could be atoms, it could be molecules or ions that are involved in the elementary step. If, for example, the elementary step just has one thing, so one atom, one molecule, or one ion producing products, we would call that unimolecular, so uni meaning one. For something that involves 2 things, so like either A plus A or A plus B, for example, creating products, we would say that this is a bimolecular elementary step because it involves 2 things. It could either be 2 of the same thing or it could be 2 different things. And finally, we have termolecular. So this is ter means 3, and this would be 3 things reacting in order to produce the products. And there's lots of possible combinations here. You could have 2 A's with a B, you could have 2 B's with a C, you could have all 3 A's. So like lots and lots of different ways that you could get termolecular elementary steps. So then how do all these multi-step reactions work together? Well, let's take, for example, a possible multi-step reaction where we have 2 reactions here, 2 elementary steps. So we have 2 elementary steps. The first step is an A reacting with a B to produce E. So we would say that this is bimolecular. And the second step, C reacts with E to form 2D. So again, 2 things. This would be bimolecular as well. Now, in terms of an overall equation, we can add these together Hess's law style. So if we take a look at A plus B reacts to give E, and then the second reaction, C plus E. So those are all our reactants, and then we would have E plus 2D as our products. Now, if you notice, E's the same on reactant and product side. So we can cancel that out. We actually have a specific term for that. So if we're producing E in one step and then using it up in the next step or in a subsequent step, we would call that an intermediate. Okay, because it's being produced in one step of our multi-step reaction, but it's being used up then in another step of our multi-step reaction mechanism. So that is an intermediate. So our overall reaction would just be A plus B plus C reacts to give 2D. Now, in terms of elementary steps, it's far more likely to have a unimolecular or a bimolecular elementary step. So if, for example, we had this overall reaction here, L plus M plus N reacts to give 2Q, a single step reaction mechanism would be really unlikely here because this would, if that's the case, it'd need to be termolecular. And in order for that to be termolecular, what would need to happen is L and M and N all need to collide together with the correct amount of energy, so are the right activation energy, as well as the correct orientation in order for this to happen in a single step. That's pretty unlikely. So usually when you see a reaction like this where you have at least 3 things reacting, it's more than likely happening through a multi-step reaction. Okay, so what does this all have to do with rates of reactions? Well, every elementary step has its own activation energy, EA, and the slowest step in our reaction mechanism is going to be our rate determining step. So this is the one with the highest activation energy. So if, for example, we take our example here of putting sand down through this tube here, you can see we got a really narrow opening here and a much wider opening here and here. So the narrow opening is going to determine our rate. So this is going to be the slowest step in our reaction mechanism, and then the other two would happen quite fast. In between those two, we have intermediates. Okay, so we can use the slow step of a reaction mechanism to determine the rate law for that reaction mechanism. So the rate law can be determined from a reaction mechanism using the rate determining step. So let's take a look at a couple of examples of how that will work. All right, so in our first example here, we're asked to find the rate law for this overall reaction here. You can see we got 5 things reacting here. So this is really unlikely to happen in one step and much more likely to happen as a multi-step reaction. So we're given a mechanism here, and what we want to focus on is that our rate determining step is our first step here. Let's highlight that because that is our slow step. So knowing that, our rate law is going to be, whoops, wrong pen, here we go, is going to be dependent on our slow step, our rate determining step. So we can take the molecularity of our reaction. Okay, so we've got our rate then is going to be dependent on the concentration of HBr. Now, there's just 1 mole in this reaction, so we're basically got a 1 up here. We normally don't write that in though, right? Because that doesn't normally go in a rate law. But I'm going to put it in just to stress it. And then we also have a 1 in front of our O2. So we have O2 to the 1. So really, when we're writing this out, we write rate is equal to K times HBr times O2 concentration. Okay, and this would be our rate law for our particular reaction. Now you can see we can't get a rate law directly from our overall reaction because we don't know what the mechanism is. We would need experimental data if we wanted to figure this out, or if we know the reaction mechanism, we can come up with it from our rate determining step. All right, so let's look at another example. We've got this overall reaction here, and we're given a reaction mechanism where now our rate determining step is our second step, our slow step. Okay, so what we got to do here is, again, we're determining our rate law from our rate determining steps. So we've got a 1 here and a 1 here again. So we've got NOBr2 to the 1. I'm not going to put the 1 in though because we don't need to. And then we've got NO to the 1 as well. Now, the thing we need to recognize here is that NOBr2 is actually an intermediate. So it's used here, but it's also produced in our first reaction. It's also not present as one of the reactants in our overall reaction, and we always write rate laws based on the reactants of our overall reaction. So we need to get rid of this NOBr2 from our reaction. And so what we're going to recognize here, I'm going to put this in red, is that NOBr2 is dependent on a Br2 and an NO reacting. So we can actually substitute out an NO and a Br2 here for our NO Br2. Okay, so I'm just subbing in that. And then we also have our NO still in there from our other part of our reaction. Okay, so at this point then we can see we've got two NOs now, so let's just simplify this a little bit. The rate is going to be K times NO squared times Br2. It is a coincidence that the 2 and the 1 match up with this. It's not always going to work out that way because, as we know, we cannot find a rate law from an overall reaction. We need to figure it out from either experimental data or from a reaction mechanism. So this is just a huge coincidence. Okay, finally, what we need to do is just talk a little bit about an energy profile for a multi-step reaction. So let's start out with an exothermic example. So I'm going to draw in our lines for our reactants. I'm just going to write R for reactants and P for products. So let's say for this particular reaction, exothermic, so our delta H is negative. Let's say our first step is our slow step. So that's the one that's going to have the highest activation energy. It's going to create some intermediate, and then it'll go through a second step here, like so. So what can we label on this? Well, remember the peaks of each of these two steps will be our transition states. So both of those stars are a transition state. The first one for the first step, the second one for the second step. And then down here at this point here is where we would find our intermediate. Okay. And we can also add in our activation energy. So remember, our activation energy comes from where our line for reactants is up to our transition state. So the activation energy for the first is there, and then from the intermediate to that peak is there. So you can see the activation energy for step 1 is much larger than the activation energy for step 2. So this would be our slow step, and this would be our fast step. Okay, just to kind of show you a different spin on this, if we do, let's say, an endothermic reaction. So we'll have reactants going to products here. Our delta H is positive. And let's do our first sort of step is going to be our slow step. Maybe let me just get rid of this out of the way for a second. So we'll do our first step as our slow step. We'll make an intermediate, and our second step, or sorry, our first step, let's make fast, and then our second step slow. So what can we label in here? Well, here's our activation energy. This is our intermediate. That's a transition state, and that's a transition state. And then here's our second activation energy, which is much larger, meaning that that's going to be our slow, and that's going to be our fast step. Okay, and then if we want to label back in our delta H, I'll put it over here. So delta H is positive, meaning that that's an endothermic reaction. So important that we're able to label our reactants, our products, our transition states, our intermediates, our activation energy, our delta H's, and then also including potential energy on and our reaction coordinates on our axes. So these are all important pieces of an energy profile for a multi-step reaction. So that's how we use reaction mechanisms, multi-step reactions to determine rate laws. That's it for this video. We'll see you in the next one.